Welcome to the deep dive. Today, we're tackling something really quite remarkable in, the molecular world. It's this bond between Avidin and Biotin. It's incredibly strong.
Oh, incredibly. We're talking about a binding affinity, that co-value. It's huge.
10 to the power of 15 per molar, right? Which is just hard to even grasp.
It really is. To put it in perspective, that's about 1,000,000 times stronger than how most antibodies bind to their targets. 1,000,000.
Wow. Okay, so molecular superglue, basically.
You could definitely call it that. And what's fascinating, and what we're digging into today, is how people thought about using that strength.
Right, that'll harness it.
Right.
Especially for things like medical imaging.
Exactly. Trying to get better pictures inside the body by targeting radiolabels more effectively.
And for this deep dive, we're actually looking back a bit at a research paper from 1987.
Yeah, investigations of Avidin and Biotin for imaging applications. It's really interesting to see the early thinking.
Because getting clear images with radiolabeled antibodies, say for tumors, that's always been tricky, hasn't it?
Oh, absolutely. Still is in many ways. The big problem is the signal-to-noise ratio, or target-to-non-target ratio.
Meaning you get radioactivity where you want it on the tumor.
But you also get a lot lingering in the blood or taken up by the liver, the spleen, healthy tissues.
Which makes the image kind of fuzzy, less clear.
Precisely. Things like, poor blood flow in some tumors limit how much antibody gets there in the first place. Plus, the body breaks down the antibodies.
Right, releasing the label where you don't want it.
So the core idea in this paper was, what if we could separate the targeting step from the labeling step? Use Avidin Biotin as a kind of two-stage rocket.
Okay, that sounds clever. So let's back up. Avidin and Biotin, the basics. What are they?
Right. So Avidin, it's a protein found in egg whites, famously.
Right.
And it's pretty big, molecularly speaking, about 66 kilodaltons. Biotin, on the other hand, is tiny.
That's the vitamin, right? Vitamin H.
Exactly. Vitamin H, only around 244 daltons, much, much smaller.
And Avidin has, 4 binding sites?
4. Yep, it's tetravalent. Think of it like having 4 incredibly sticky patches specifically designed to grab biotin.
And they grab it fast and hold on tight.
Extremely fast formation. And that bond, as we said, is incredibly stable. It laughs off changes in pH, organic solvents, stuff that would normally mess up proteins. Absolutely. Competitive binding assays using labeled Avidin to detect tiny amounts of something tagged with biotin. It's a standard tool.
And they'd even thought about using it for drug delivery before this.
Yeah, linking Avidin to a drug and then using a biotin-tagged antibody to guide it to a tumor cell. The potential was recognized early on.
Okay, so it works great in a test tube. What about using it inside a living thing, in vivo? Were they worried about safety?
Well, they seemed optimistic. Biotin's a natural vitamin, so that seemed pretty safe at low levels.
Right.
Avidin is foreign, it's from eggs, but the thought was at the concentrations needed for imaging, it would likely be okay, non-toxic.
And the biggest hope was that the bond itself would survive.
Exactly, that the super strong interaction would hold up inside the complex environment of the body, that it wouldn't just, fall apart.
Makes sense. Okay, so they had this potential tool. The paper explored 2 main strategies to use it for imaging. Let's take the first one.
Right. Approach 1. This involved modifying the antibody first.
How so?
They chemically attached biotin molecules to the antibody, like putting little flags or handles on it.
Okay, so the antibody has biotin handles. Then what?
Then you inject this antibody, the biochelated one, but it's not radioactive yet.
Ah, okay. Step 1. Send in the guide molecule.
Precisely. You give it time to circulate, find its target, maybe a tumor, and bind there.
Let the handles accumulate where you want them.
Exactly. Then step 2. You administer Avidin, or streptavidin, that is carrying the radioactive label.
And that seeks out the biotin handles waiting at the target site.
That's the idea. It latches onto the biotin, and boom, you've localized the radioactivity right where the antibody went.
You mentioned streptavidin there, too.
Yeah.
What's the difference?
A very similar binding strength to Avidin, but streptavidin comes from bacteria, Streptomyces avidini.
Okay.
And the key difference highlighted was that streptavidin isn't glycosylated. It doesn't have the sugar chains that Avidin does.
And why does that matter?
The thinking was those sugars on Avidin might cause it to stick non-specifically to other tissues, like the liver. Streptavidin might have less of that background stickiness.
Leading to a cleaner image, potentially.
Got it.
What label did they use?
They used indium-111, Watoinen, and they attached it using a chelator called DTPA. basically a molecular cage, to hold the radioactive indium onto the Avidin or streptavidin.
And they tested this first with beads.
Yeah, a clever model system. They implanted little agarose beads that had biotin attached into mice.
Kind of like a tiny artificial target.
Exactly. Then they gave the labeled Avidin or streptavidin.
And did it work? Did it improve the signal?
It did. They saw significantly better target to non-target radioactivity ratios compared to what you'd expect if you just labeled the antibody directly in a conventional way.
So, proof of principle, basically. Promising.
Very promising early results for that first approach.
Okay, so that's strategy one. What was the second main approach they looked at?
They essentially flipped the script. This time, they attached the Avidin directly to the antibody.
So the antibody itself is carrying the Avidin now.
Right. The Avidin antibody conjugate is step one. Inject that, let it find the target.
Okay. Then what's step two?
Step two is injecting radio-labeled biotin.
So the radioactive part is the small molecule this time.
Exactly. And the potential big advantage they saw here was clearance.
How so?
Biotin is small. If the labeled biotin doesn't find any Avidin bound at the target site,
It should get filtered out by the kidneys really quickly.
that was the expectation. Rapid clearance of unbound radioactivity, leading to potentially much lower background noise in the image.
That sounds really appealing for getting a sharp picture.
It does. Less radioactive haze, potentially.
Did they test this one with beads too?
Yep. This time they used beads coated with Avidin, implanted them in the peritoneum, the abdominal cavity, of mice.
Okay.
Then they injected the in-labeled biotin into that same cavity.
Did it stick to the beads?
It did. Strong localization of the radioactivity right on the Avidin beads. It supported the idea that the labeled biotin would bind the target and the unbound stuff would hopefully clear out fast.
So two different two-step strategies, both showing promise in these early beads models. But I imagine actually doing this raises some practical issues.
Oh, absolutely. Like step one, you're attaching this big protein Avidin or streptavidin to your antibody. Does that change how the antibody behaves in the body?
Yeah, does it still find its target properly? Does it go to weird places? Its biodistribution.
Exactly. That was a key question. They did studies in mice comparing directly labeled antibody versus the antibody conjugated to streptavidin, where the label was on the streptavidin.
And what did they find? Did adding streptavidin mess things up?
Surprisingly, not really. The tissue distribution was pretty similar for both, except for the heart, apparently. But overall, it suggested attaching the streptavidin didn't drastically alter the antibody's journey.
Okay, that's good news. What about the clearance speed of the radioactive bits themselves? We talked about biotin being fast.
They confirmed that. Avidin-labeled biotin cleared the body rapidly in mice.
Which is great for that second approach.
Right. And they also showed, logically, if you attach biotin to bigger proteins, it slows down that clearance. Bigger things hang around longer. Understanding that is key for timing the steps.
Makes sense. Now, another thing. Avidin has 4 binding sites, tetravalent. If you're mixing it with antibodies that have biotin handles, couldn't it act like glue and just clump everything together? Make big aggregates?
That's a really sharp point. Yes, that's a definite risk. Cross-linking. Those clumps might not work well.
So how did they deal with that?
They found a neat trick. After letting the Avidin bind to the biotin-elated antibody, they added an excess of free biotin. To block up the remaining empty binding sites on the Avidin.
Exactly. Stops it from grabbing other antibodies and causing a big mess. Saturate the extra hands.
Clever. Okay, one last check. The core bond itself, Avidin biotin. How stable is it really in something like blood serum?
Yeah, they tested that too. Serum stability studies.
Man.
Rock solid. The Avidin-biotin bond held up extremely well over 24 hours in serum. Minimal release of radioactivity.
Okay.
Now, interestingly, when they looked at labeled biotin detaching from Avidin beads in serum, they did see some release of the indium-111.
Oh, so the bond did break.
They didn't think so. Their conclusion was it wasn't the Avidin-biotin bond breaking, but probably another protein in the blood called transferrin.
Which binds metals.
Right. Transferrin might have been sort of stealing the indium-111 off the DTPA chelator, a different mechanism called transconflexation. Important nuance.
Okay, got it. So it tackled these potential problems. Now for the really exciting part, the actual imaging studies, did they get pictures? They did. This is where you really see the potential. In one study, they put those biotin-coated beads under the skin of a rat.
Okay.
Then they injected in-labeled streptavidin intravenously into the bloodstream.
And watch where it went?
Yep. And over time, they could clearly see the radioactivity building up right at the site of the beads, a direct visualization of the targeting.
That's cool. Visual proof. But they needed something more like a real tumor target, right? Not just beads under the skin.
Exactly. So they did another study using protein A-coated beads.
Protein A. Why that?
Protein A is known to bind very strongly to antibodies, specifically the FDC region, the tail end.
Ah, so the protein A bead acts like something an antibody would stick to, a tumor mimic.
Precisely. They put these beads in the peritoneum of mice. Then, step 1, they injected an Avidin conjugated antibody,
Which would stick to the protein A beads via its FC region.
effectively coating the tumor beads with Avidin.
Setting up the target. Then step 2.
Then they injected the in-labeled biotin into the peritoneum, the second strategy again.
And the crucial comparison was
Against control mice that got the same Avidin antibody conjugate, but where the indium-111 was attached directly to that conjugate, the conventional one-step approach.
Right. So did the two-step method win?
Oh yeah, big time. The target to non-target ratios were significantly improved in the two-step group.
How much improved?
They looked at the radioactivity on the beads, or rather the intestines where they lodged, compared to organs like the liver, spleen, kidneys. Ratios were often better than 10 to 1.
That's pretty good.
And for the spleen, it was even better, often over 100 to 1.
Wow. Compared to the direct labeling.
Much better contrast than the direct labeling controls. It really suggested that unbound labeled biotin was clearing out, leaving a much cleaner signal at the target.
It's a huge potential improvement for actually seeing things clearly.
Massive. And they didn't stop there. They did another protein A bead study, this time focusing on the timing.
The time gap between injecting the Avidin antibody and the labeled biotin.
Exactly. They tried different intervals, 0 hours, basically simultaneous, 2 hours and 8 hours apart.
Did waiting longer make a difference?
It made a huge difference. The longer the interval, the better the target-to-organ ratios got.
Really?
At the 8-hour time point, the ratios for the spleen and kidneys were over 1,000 to 1.
Get out. 1,000 to 1 ratio.
Absolutely stunning improvement. It suggests giving that unbound antibody time to clear and the bound antibody time to really settle in before adding the label makes a massive difference to reducing background noise.
That is just remarkable. From an experiment in 1987.
It really highlights the potential power of this two-step pre-targeting idea.
So wrapping this up then, it seems crystal clear from this early work that the Avidin biotin system showed, just enormous promise for improving how we target radio labels.
Absolutely. Better localization, potentially much clearer images.
By separating the targeting antibody from the radioactive payload.
And leveraging that incredibly strong, fast bond.
And especially that second approach, Avidin antibody first, followed by the small, fast-clearing labeled biotin that really delivered those incredible target-to-non-target ratios in their model.
Yeah, the results from that strategy were particularly striking. The stability and the kinetics of the Avidin-biotin interaction were key.
It's fascinating stuff.
Yeah.
And it really makes you wonder, doesn't it? This was the late 80s, so the thought for you, our listener, has to, what happened next? Given these amazing preclinical findings, what were the hurdles? What were the breakthroughs in trying to actually get this kind of technology into the clinic over the last, 30-plus years?
It's a great question. How did this elegant molecular trick fare in the real world? How is it being used or adapted today? It's a perfect example of how fundamental science can spark really innovative medical ideas.
Definitely leaves you wanting to know more.